Hello, everyone, and welcome. Thank you for joining us in this episode of Spectroscopy in Action, our live webinar series. My name is Paula, and I'm the Marketing Account Lead for Edinburgh Instruments. And today I'll be joined by Angela, our Raman Product Manager, and Matthew, our Raman Application Scientist, who will be discussing the advanced spectroscopic characterization of semiconductors. So today they will be talking us through several case studies showing how multimodal microscopy is being used in both research and industry for semiconductor research. This includes simultaneous Raman and photoluminescence imaging in silicon wafer, correlated Raman and photoluminescence imaging of gallium nitride LEDs, carrier dynamics in perovskites using FLIM, and more. Matthew will also show us how the RM5 and RMS1000 microscopes are configured for these workflows. At the end, we'll have a live Q&A session, so you'll be able to ask any questions that you might have. Hope you enjoy this webinar, and I will now pass over to Matthew and Angela to get started.
Thanks, Paula. So to start with, I don't think we need to do the introduction to what we have coming up in this webinar, as Paul has quite clearly gone through it all. However, I will quickly touch on the products, but I won't take up too much of the time so that Matthew can get into the interesting part. So we offer two multimodal instruments at Edinburgh Instruments that are perfect for looking at semiconductor research. We have an RM5, which is a benchtop research grade instrument, and we can do both Raman and steady state photoluminescence with this. We can integrate up to three lasers, and two detectors. And the importance of the dual detector here is that you could have a CCD camera for detecting your visible photoluminescence or also your Raman peaks, and then an InGaAs for detecting the near IR photoluminescence that we typically see in example for silicon. So this is our smaller instrument and mostly used just for Raman, but we can also integrate that second detector for near-infrared PL as well. Moving on to our second instrument, this is the RMS1000. So this is a truly multimodal microscope. It's been designed to incorporate as many techniques as we physically can. So with this one, we can now include up to 5 lasers. We can still do your Raman and steady state photoluminescence, but we can now incorporate fluorescence lifetime measurements. And this can be both fluorescence lifetime and phosphorescence lifetime measurements. And another distinct advantage of this is we can offer wafer mapping. So we can integrate large stages that can go up to 12-inch wafers, which Matthew will give more details on throughout the talk. And we can also include a long spectrograph. So this is an 800 millimeter spectrograph that we can include. And this is perfectly suited for looking at the semiconductors where your Raman peak shifts are so small and tiny that you really need the highest of spectral resolution. I won't bore you anymore with the instrument details and hand over to Matthew to get into the interesting part.
Thanks, Angela. Good morning, everyone. Before we get into the case studies, I thought it'd be good to go through why you'd want to use multimodal microspectroscopy for research. So I'll explain a little bit about Raman and PL, maybe some other techniques. So first, let's look at Raman. So Raman is a technique with extremely high molecular specificity. Each Raman active semiconductor material produces a unique spectrum that can be used for chemical identification and for structural identification. So by structural identification, I mean that say you have a semiconductor with different crystalline polytypes. These will have unique band patterns, as do any organic impurities on the surface of your semiconductor. Variations within the bands within your semiconductors can also provide a lot of info. So for example, if the intensity of your semiconductor Raman band changes, this can be indicative of changing thin film thickness across your sample, whereas changes in peak position and widths are good measures of strain and crystallinity variations. So it's very easy to see variations with Raman. Now, what about photoluminescence? So whilst Raman is used primarily for structural identification, PL is more used to measure the band gap and the radiative efficiency of a material, which are both very important optoelectronic properties that you'd want to know about. PL bands are sensitive to strain and crystallinity, but the interpretation of them comes more down to how these phenomena influence the material's optoelectronic properties, if you're interested in that. So alone, both of these techniques are very powerful. However, when we combine them on the one platform, even in the same spectrum, we can simultaneously obtain both structural and optoelectronic performance data from the same sample. So this can give you a much more complete picture that neither technique alone would be able to provide. Raman and PL aren't the only techniques that can be coupled into our multimodal platforms. So say you're interested in analyzing crystalline symmetry and layer stacking and 2D semiconductor materials, then second harmonic generation could easily be added alongside Raman and PL. So we did cover this one in depth more in our recent 2D materials webinar. So I suggest Craig to add a little link when this goes up on YouTube. Fluorescence lifetime imaging is another technique we can couple in. So this is highly complementary to standard PL imaging, but in many ways it's a lot more useful because it provides information about recombination pathways and charge carrier dynamics in semiconductors, which are very important optoelectronic properties, especially if you're looking at display materials or photovoltaics or things like that. With those things in mind, it's also easy to integrate more direct performance techniques into the system. So you had an LED or an OLED, we could couple in steady state and time resolved electroluminescence. Or if you were working with photovoltaics, we can also couple in photocurrent imaging. So in the example on screen, we have a sample and we raster the laser over it. And at each point, we get the photocurrent as well as Raman and PL spectra. So I hope you understand the benefits of the spectroscopic techniques a bit better. But what's the benefit of putting them through a microscope essentially? So the key benefits of this are the ability to probe submicron sample features and to do imaging. So when you focus the Raman or PL laser through an objective and collect the resulting emissions through a confocal pinhole, you have virtually diffraction limited imaging capabilities, so submicron. So we can couple this spatial resolution with the high chemical and structural specificities of Raman and PL, and then we can correlate structure performance of semiconductor features in 2 or 3 dimensions at the submicron level. So we now have hopefully a better understanding of what multimodal microscopy is and how it can benefit semiconductor research. So let's now turn to a case study that shows how performing simultaneous Raman and PL allows us to correlate defect structure to radiative efficiency in silicon. So I'll start the discussion of this case study by covering the Raman spectrum of silicon and semiconductors in general. So in semiconductors, Raman modes occur through the inelastic light scattering by phonons, which are the elementary excitations and the quantum mechanical treatment of crystalline lattice vibrations. So what does that mean? The image on screen kind of shows that. So that shows a phonon mode on the surface of a crystal. So when the atoms within the lattice undergo coherent oscillations, a vibrational wave propagates through the crystal. In silicon, the main Raman mode at 520, which you can see on screen, it's labeled the LO phonon mode. That occurs when a 100 or 111 silicon surface couples to an optical branch phonon. And that's how we get a Raman spectrum in semiconductors. So as we previously discussed, this isn't a static fingerprint. It's sensitive to even the most minor of perturbations in the material structure, particularly that phonon mode. And we can obtain this spectrum really easily. So we can use excitation between 405 nanometers and 830 nanometers and just detect it with a CCD camera. So now onto the PL of silicon. Silicon has an indirect band gap, and the PL emission occurs at roughly 1140 nanometers. So this can be detected and imaged on a Raman microscope, a multimodal microscope rather, but the output is heavily detector dependent. So CCD detectors have a high quantum efficiency in the visible region, but they begin to drop off in the near-infrared, so approximately 1000 nanometers. In contrast, an InGaAs detector, specifically designed for near-infrared sensitivity, maintains a high quantum efficiency across the near-infrared range, so from 1000 nanometers to 1600 nanometers. So if you detect silicon PL with both detectors, you'll see a big difference in the intensity and spectral position of the measured signal, as you can see on screen. So these spectra were both acquired with a 532 laser on the same part of the sample. We just use different detectors. So when you use an InGaAs, the PL peak centered at about 1120 in this case, which accurately reflects the intrinsic emission of the silicon close to the band gap energy. But when you use a CCD, the PL peak kind of blue shifts and is centered at 980. So this is an artifact of the rapidly falling quantum efficiency of the CCD. However, in practical terms, You could use a CCD and do PL mapping and still get value from it. So especially for relative intensity comparisons across a wafer or chip, if you wanted to track how your radiative efficiency was changing, you could do that. But if you want accurate PL position width measurements, you'd of course need an InGaAs. So if we want to combine Raman and PL together, we could use an near-infrared 830 laser with a CCD to get Raman and PL intensity in a single scan. With a system equipped with both a CCD and an InGaAs, you could acquire Raman and PL sequentially, but not simultaneously, because you'd have to change optics between measurements. So in this case study, we did simultaneous Raman and PL. So we used an 830 laser and a CCD detector on a silicon sample. So when we couple the simultaneous spectral modes with automated fast high-resolution imaging, we can build up images that correlate silicon structure and the optoelectronic properties of the semiconductor. So before getting into that, I'll go on a quick tangent about spectroscopic imaging. It's not really a tangent because I put this in, but each pixel within an image contains an entire spectrum. So that consists of our Raman PL signatures, and then we can create image contrast across a sample to identify features of interest by selecting a numerical feature of the spectrum. So this could be the intensity of a peak, position, the width, the ratio of two peaks, the x-axis splitting between two peaks, or even chemometric parameters that basically describe the entire spectrum with some number. So this is exactly what we've done with a silicon sample. So we use multivariate chemometrics, namely PCA, to create chemical contrast and identify these any structural optoelectronic defects and explore the relationships between the Raman and PL. So a quick explainer on PCA. So this takes the thousands of wavelength-dependent intensity values in each spectrum, and it compresses them down into a small number of principal components, or PCs. Each PC has a score, which we can use to generate images, and a loading spectrum, which shows how Raman and PL features contribute to variation within the image. So essentially, instead of us going to look for the variation within the image, so look, maybe we want to check the intensity of the silicon peak, position of the PL peak, PCA basically finds that for us, both spatially and spectrally. So what does it show in our silicon sample? So I would draw your attention to the feature within inside the blue ellipsoid. So during imaging, this feature displayed a drastically different spectral response. It was obvious that it wasn't indicative of a contaminant or an impurity. And it was just the PL and Raman peaks were very different to the surrounding silicon, so we designated it as a defect. When we perform PCA, we take PC1 and PC3. PC1 separated regions of higher PL, which had positive scores on the loading spectrum, from dampened PL relative to Raman, which had negative scores. We know this because in the PC1 loading spectrum, the Raman feature is below 0, it's negative, and the PL feature is positive. So in this image, the features that are negative have basically lower PL relative to Raman, so the red purpley regions. And then when we look at PC3, this shows changes in the Raman phonon mode shape and position. So this is indicated by the opposite signed Raman features and the PC3 loading plot here. So you have a peak going down, a peak going up. So that shows that the peak's changing essentially. So fancy maths, what does it all mean physically? So it shows that in the same defect, we have a change in the position of the Raman phonon mode and the dampening of the PL band. So this indicates to us that a change in the vibrational structure, so potentially due to strain or dopants, coincides with a reduction in the radiative efficiency of the material. So here, PCA combined with simultaneous Raman and PL has given us both a direct and objective correlation between Raman and PL. And that doesn't require us to have prior knowledge of what spectral features to examine beforehand. So with this is kind of exploratory, but with this we could then proceed to do quantitative, strain or recombination analysis to understand the material a bit better. So let's talk a bit more about how to analyze semiconductor data in general. So our software that we can use on the RM5 and RS1000 Ramical has several native analysis tools built in, including some multivariate analysis. So you can explore trends in your maps. If you want more flexibility, we have an integrated Python IDE, which gives you virtually any advanced machine learning method, but so far we've integrated the Mahalanobis distance, that's a tongue twister, k-means clustering, non-negative matrix factorization, least squares, and different quantitative fitting approach. So the workflow can be basically simple or advanced as you need. So you can do fast trend finding in Ramical or deeper chemometric analysis in Python. And I think this is the end of this case study, but we'll give a little overview of the configurations possible for acquiring Raman and PL. So we've only really covered the simultaneous configuration where we'd use an 830 laser on a CCD. So you could just analyze silicon using Raman only. You could analyze it using PL only, and you'd still get a lot of data, or just acquire them sequentially with the two detectors. So for just doing Raman, we'd recommend a 532 laser and a CCD. We have different CCD options, which kind of enable higher sensitivity and faster imaging. So for example, the front illuminated CCD, which is standard, gives you approximately 55% quantum efficiency at the peak of the quantum efficiency curve, whereas a back illuminated CCD gives you about 95%. We can also supply electron multiplied CCDs, which boost the signal even more using multiplication gain technology, which generates multiple photoelectrons per photon, giving you even higher sensitivity and speed. If you wanted to do PL only, we'd recommend the same laser 532 with an InGaAs array. And then if you wanted to do Raman and the fully accurate PL emission data, then a system with the two detectors would be required for sequential imaging.
Thanks, Matthew. Can I just interrupt with a couple of questions that I've thought of as you were going along there?
Sure, go ahead.
So you very briefly, just as a tiny wee point there, had quantitative analysis mentioned as part of our integration of the Python EDE. What could somebody learn from doing that quantitative analysis on these sort of materials?
Yeah, that's a good question. So essentially, I'm mentioning that strain and PL can be used to track, PL and Raman can be used to track strain and doping, but if you just do Raman, all you see is a peak shift. You don't see how much strain's applied or how much doping's applied. So that the literature has several linear algebra techniques where you can take the shift in the Raman peak position and turn it into, say you were looking at aluminium gallium nitride. You want to know how much aluminium's doped within the material. You can work that out using the change in the Raman peak position. Same with strain, can be directly correlated to the GPA being applied to the sample. If you're looking at something like carbon nanotubes and want to know the diameter of your nanotubes, you can get that as an output, basically straight from the Raman data. So that's what I meant.
Perfect. Thank you. And I believe we're now moving on to an example of silicon carbide.
Yep. So silicon carbide, I'm sure anyone watching this will actually know this, but it's a critical material for power electronics. So in this case study, we'll explore how 3D Raman imaging can be used to determine both the spatial extent and the chemical nature of defects in silicon carbide, because these could lead to voltage failures or reduced performance within power electronics. So as you can probably guess, Raman is ideal for this task because each polytype of silicon carbides, of which there's about 250, has a unique vibrational fingerprint. So remember they said before that Raman is capable of differentiating different crystalline polytypes. This is really the case that I had in mind when I said that. So there are other reasons why Raman's suitable for analyzing silicon carbide. It's, there's a strain effect. There's specific modes within the silicon carbide spectrum that's sensitive to doping concentrations. So this little mode here, the LO mode, moves basically when you add more nitrogen. And of course, with all semiconductor examples, defects are revealed through either new phonon modes, shifts, peak broadening, or maybe just symmetry breaking, which creates new bands. And importantly, what we want to show here is that all these phenomena can be imaged in 2D and in 3D when using a confocal Raman. So for a better understanding of 3D imaging, before we just show you 3D data, we have to consider what the confocal pinhole does within a system. So when you have a true confocal pinhole, out of light focus is rejected, which allows you to section your sample optically in Z. So if you look at the image on screen, on the left-hand side, so image A, when the pinhole's open, light that's generated from above and below the focal plane is allowed to enter the spectrometer and be detected. That means that the spectrum you detect is essentially polluted by Raman PL signatures from structures that are out with your focal plane, which you don't want. It's problematic if your structures are small, and if you want to know the true dimensions of your structures in Z. When the pinhole's closed, the out of focus light is essentially blocked from entering the spectrometer, so the collection volume is decreased, and the resulting spectrum is more pure, and it will contain more signatures from the focal plane, like almost exclusively. So this means that we can use this with 3D movement of the stage to reconstruct 3D Raman maps of defects, and not just looking at the surface. Each voxel within your 3D volume will contain only the in-focus Raman signal, so it gives you chemically structured resolved volumes. So to do 3D Raman imaging of silicon carbide, we use 532 nanometer excitation. We'll mention the grating here because it's high resolution. We need a high resolution grating. So 2400 grams per millimeter. And we used a back illuminated CCD. So this enables us to do fast, high quality 3D imaging where we can see even the most subtle changes in the spectrum. With an EMCCD, we could probably, ramp that sensitivity up even more. So here's a region, the picture on the left, on a silicon carbide wafer where we noticed potential defects when looking at it with white light microscopy. We then generated a false color Raman image using different Raman mode peak intensities. So in green, this is a map of the TO band at 768 wave numbers, which is characteristic of 4H SiC. So this is what the wafer was advertised as. So what do I mean by 4H? So in silicon carbide, you have a silicon carbide tetrahedron, and 4H SiC, these will stack in with hexagonal symmetry. And the number 4 refers to the number of carbon layers within the unit cell. So, so for the structures on screen, it's C, essentially. So the regions that we thought were defects, they showed a different band at 795 wave numbers, which wasn't on the 4H silicon carbide. So we assigned this band as the TO band of 6H SiC. So by 6H, we mean it also has hexagonal symmetry, but in this instance, the unit cell has 6 layers of carbons. So through the Raman spectra, we're able to characterize the chemistry of the defect and say that it's likely a polytype inclusion. And it's a polytype inclusion because it's just a different polytype of silicon carbide, but it's maybe not what the manufacturer wants to be in their wafer. So when we look through basically the Z dimension of the 3D Raman map, following the peak intensity of our defect through the volume, we see that the inclusion isn't just on the surface. It forms a pipe-like structure, which extends more than 3 microns into the bulk of the wafer. These are really well known in industry and are generally referred to as micropipes. So putting it all together, 3D Raman imaging can essentially tell us both the chemistry of the defect and its 3D morphology, which is very powerful for material characterization. It's very relevant for silicon carbide device reliability because micropipes and inclusions are known to affect wafer quality, long-term performance. You essentially don't want these at all.
So on the 3D side of things, how deep can you go into a sample, and is there anything that you can choose within your setup that's going to affect like the sort of configuration that will affect your 3D mapping, or also a surface? Because I guess the takeaway from the confocality is you're looking at a very exact Z location in the sample.
Mm-hmm. There's different factors at play. So if you want to be able to probe through your sample, you'd have to use like a green or red laser. If you want to have very specific surface analysis, and then you'd want to move down towards blue or the UV. When doing 3D imaging, there's different things to consider. So you have your objective lens, which you want to have a high NA. So with a 100x, we can probe about 100 microns into the sample, but that should be caveated by saying, the deeper you go into a sample, the more your laser spot's blurred. So I would recommend if someone's wanting to do like really deep imaging, they should compare the 3D Raman imaging to potentially doing like a 2D cross section and seeing how they compare. As part of a research project.
Great. And next up, we have some gallium nitride to take a look at. I'll hand back over to you, Matthew.
We sure do, Angela. So for this case study, the question we set out to ask was, can we correlate structural strain with radiative efficiency in a blue LED? So there's different challenges to analysing gallium nitride than there are to silicon carbide or silicon, which will become clearer in a second. So first, the Raman spectrum. The main feature in gallium nitride is what is called the E2 high mode at 568 wave numbers, and this shifts very readily under compressive or tensile strain. So an increase in the peak position, if the peak position moves to the right, this indicates compressive strain, which means that the crystal structure is becoming more compressed, obviously, and a decrease in the peak position points to tensile strain. So the atoms are being pulled apart. In this Raman spectrum, we also see substrate contributions from the underlying sapphire. So kind of analogous to maybe if you had an impurity, but also on the underlying substrate if it's just an epitaxial layer. But obviously, with all the other examples, if the wafer was low quality, we'd be able to see defect-induced broadening, all that. So like before, PL tells us about the optical quality of the material. So gallium nitride is challenging because it exhibits band edge emission at 3.41 electron volts, which is approximately 365 nanometers, as well as defect and InGaN related PL bands at lower energies. And InGaN sounds a bit random, but I'm pointing to that because in this LED, the InGaN was what was at the PN junction and responsible for the blue emission. We can also differentiate doping types with PL because P doping can reduce the PL of gallium nitride, the near band edge emission. So to correlate Raman and PL in this study, we configured the RMS with a red laser for Raman and a UV HECAD laser for PL, both running through the same spectrograph and stage. So in this instance, we perform both modes sequentially through the same 225 millimeter spectrograph. So that means we can switch between strain mapping and PL mapping. If we'd run this on a system with an 800 millimeter spectrograph, we could basically do this sequentially with a 325 nanometer source. So we'd get the Raman and the PL in the same spectrum. We basically can't do Raman through the 225 spectrograph with the UV laser because UV lasers have a naturally lower spectral resolution. So you need the longer spectrograph focal length to improve that. So in this slide here, we're specifically looking at Raman mapping across the LED structure. So we track both the peak position and the area under the curve of the E2 high phonon mode, and we can build up a detailed picture of the strain distribution and just the structure. So what you're seeing is essentially a structural map of the LED. So the color scale here highlights compressive strain regions in green and tensile regions in white. So it's a measure of, across the map, how is the crystal lattice being stretched or squeezed at different points on the device. So this is very important for LEDs. So strain directly affects the band structure of GaN, which we'll see in a minute. So this impacts the efficiency of the light emission. So in areas under compressive strain, for example, you may have trapped charge carriers that that scatter phonons more strongly. So it changes the overall optical performance of the material. So by mapping it in this way, we can pinpoint structural variations across the P-GaN, the N-GaN, and the N-GaN junction, which is where the light's actually generated. So Raman gives us a direct, non-destructive tool for linking strain to device functionality. So when we switch to PL mapping, we get a view of the optical performance. So what stands out in the PL map is how the PL intensity varies in direct correspondence with the strain map from Raman. So the regions, kind of this top right corner in the yellow, that we just saw that were under compressive strain show a really big suppression of the near band edge PL. So it means that these strained regions are less efficient at converting charge carriers into light, lowering the overall optical quality of the device. And of course, it's an LED, you do not want any part to have lower optical quality. So we can also distinguish the different layers. So the P-GaN in the middle shows inherently lower PL efficiency because of magnesium doping, which magnesium doping essentially introduces acceptor levels within the semiconductor that compete with radiative recombination. They're very deep. In contrast, the InGaN junction emits strongly around 2.38 eV, which is about 510 nanometers. So slightly blue shifted compared to the surrounding material, and that is the signature of the functional LED device. So it's emitting at the PN junction, essentially. When we overlay these data sets, the story is extremely clear what's going on. So Raman tells us where the strain's present, where the lattice is distorted, and where defects might be creeping in. And then PL tells us about the performances. Like where's the device bright, where's it dim, how efficiently is it working? So by correlating the two, we see a one-to-one relationship. So higher strain, lower PL. And that's a direct structural functional one. So for industry, it means you could screen devices for both structural integrity and optical performance before they're packaged, saving time, cost. For research, it's a very good way to study how strain engineering or doping impacts device behavior at the microscope. So, I've mentioned strain here as a negative thing, but a lot of semiconductor R&D is actually about engineering strain to see if you can get some interesting properties.
And in this case, between the two, you've used different objectives between the photoluminescence measurements and the Raman objectives. Can we still say that those are truly correlative, or what could we have changed to sort of make sure that they were truly overlapping in spatial resolution?
Yeah, absolutely. So the lasers were different in this case. So one was a red, one was a UV, and the objectives were different. One was a 0.9A numerical aperture, and one was 0. So they will naturally have different focal points. So we have to correct for that in the software. So we do correct for chromatic aberration within the software. So they'll be on the same Z plane essentially. As for the sample spot size on the sample, they probably will be a bit different using different lasers and objectives. But this is where we'd recommend doing everything sequentially with the UV laser and the 800mm spectrograph.
Perfect, thanks. And the examples we've sort of gone through so far have been very, I would say, more geared towards the academic, still research stage level, looking at your samples. But we're now going to introduce how we can take this a step further as we're moving into industry, and how we can integrate wafer and mapping an entire wafer into our software.
Yep. So as Angela said, we're now going to scale up from single devices to entire wafers. So the semiconductor industry is basically built on big 300mm wafers, which they form the foundation of thousands of individual devices. So at this stage, you've done your R&D, you have your wafer ready to go. What's critical at this stage is that your wafer is uniform. So you don't want any variation in strain, doping, or optical quality across the wafer, because this can translate directly into yield losses further down production line. If a lot of your wafer strained, then it can't really be used. So with the RMS 1000 wafer system, we can apply the exact same Raman and PL analyses that we've just discussed, but do them across a full wafer surface. So we have a feature in Ramico called Wafer Map, and this makes it manageable to automate the scanning and the data handling. So you essentially get processed wafer maps that highlight where the wafer can meet spec and where it doesn't meet spec. So I've got a little video here of how it works. I hope it plays. Can you confirm it's playing, Angela?
Yeah, it's playing.
Yep. So this is our software Ramico. So I'm clicking up here to silicon wafer. So that's our wafer map feature. And in this feature, we can essentially just load plate templates. So this one only has 4-inch wafers, but you can. Oh, I'll put it back to start. Sorry. You can basically any wafer size you can input it, and as long as the stage is big enough to cover the whole wafer, it will map the whole wafer. We can also just set our mapping resolution on it. We can either do the full wafer, or we can just do discrete points on the wafer. So maybe you've done a lot of fabrication. You know your wafer is relatively uniform, relatively good. Maybe you just want to do a line across it. Maybe you just want to do select points. I'll just pass. So in this section, this is more in line with our regular Ramico window. So we can select the laser power, the grating, which controls resolution, as we said before, spectral resolution, our pinhole, and detectors if you have multiple. So you can just select them on the software. They're automatically selected. And then what you do is you set the exposure time for your spectrum, whether it's Raman or PL, and then you can start your map. And I've moved a lot faster in the video. So now we have our spectrum. So this is carbon nanotubes on silicon. So we can essentially track how the carbon nanotubes are distributed across our silicon wafer. And we'll just zoom in on the carbon nanotube peak to map the intensity of that peak. Now we've sped up a little bit, but you can see it's mapping the whole wafer. We have a full spectrum at each point. So as we've done with our small devices, we can just take this data set and do whatever on it to work out what we want. I'll just stop there and I'll skip to the next slide where I've got more about the data analysis. So now we're more concerned about uniformity. So how do we go from a data set containing hundreds or maybe thousands of spectra to just a simple Boolean, this wafer passes or this wafer fails? So it's actually very easy using just spectral response statistics. So you can define tolerance windows for parameters like Raman peak position, PL intensity, line widths, or even more advanced metrics like Pearson correlation or PCA distancing. So the software would then check every spectrum across the wafer against those thresholds. If more than a set percentage of the spectra, so that's essentially the area on the wafer, falls outside of the tolerance, the wafer would then fail. If they're within tolerance, then the wafer would pass. So these tolerances and thresholds are completely customizable. You can set them to your own process requirements. So on the screen, we've got failures that are due to the wafer, failures on the wafer due to intensity in yellow, peak position, which in this example, none failed, peak width, which is in pink, and then we have a PCA distancing metric, which also caused a fail. And this example on screen is different actually. So this is for silicon PL that was detected using an in-gas array. So what it's telling me is that the band gap didn't change, but there's something else going on in the spectra that are causing peak width changes, and we'd need to explore the PC a little bit more to know what's going on. But these chemometric ones are really good for things like contaminants. If you're not looking at a specific peak, you just want to look at how the whole spectrum changes versus the mean, then you would use this. So this is a very sensitive method for ensuring uniformity and quality at scale. And before we get on to the webinar conclusion, I don't know if you have any questions about the wafer, Angela.
Just for setting those tolerance levels, how do you go about knowing them? Is it sort of industry standards, a case of reviewing literature? Does it vary from, the end goal of the wafer as well?
I imagine that when setting up a Raman microscope in a fab, the user would have a large number of wafers that they know are very good through other techniques. So I guess it would be building up a statistical data set of Raman and PL signatures that are good, uniform, and making the tolerances from that.
So that brings us to the end of the presentation part of the webinar today. I'll hand back over to Paula, who can let us know if you've asked any questions throughout, and also if any questions come to mind later, you can still get in touch with us at any point.
Thank you, Matthew and Angela. That was really interesting and insightful. And we do have 2 questions so far. Feel free if you've got any others to add them in while we discuss these ones. So the first question is, what would you say is the main advantage of Raman PL over traditional techniques?
So for me, I would say the fact that it's non-destructive and that it has high chemical specificity. So it has advantages over other microscopy techniques. Like a lot of manufacturers will just look at the white light image and look for visible defects. This gives you actual structural information about that. But also the fact that it's non-destructive. So other techniques like mass spec or auger electron spectroscopy, you have to sacrifice some of your wafer. Whereas if you set up your wafer map correctly, you don't have high wattage of laser power on your sample. You can basically maintain 100% of your sample. So that's what I would say.
Yeah, and I think an important part with the full wafer mapping, when we're talking about going into fabs, is these can also be integrated with microscope providers that already have automatic wafer loaders. So you also physically never have to touch your wafers. These could be integrated with an automatic wafer loader, and then there can be a vacuum on that wafer stage to keep the wafer completely secure. So you're basically eliminating the need for anybody to go in and potentially get a fingerprint on there or drop a wafer or everything else in a fab that needs to be as automated as possible.
Been there, been there.
Yeah, that's great. Good to know that it keeps, the sample safe as well as giving as much information as we get from them. Another question we have is it possible to get information from organic semiconductors about charge relaxation?
So I would assume that for that one, you'd be thinking about doing FLIM. So as the basically in a semiconductor, variations in the lifetime can tell you about how the charges are recombining. If that's what's meant by relaxation, I'm thinking recombination. So in that case, you'd want to do FLIM, but we can also do the wafer map setup I showed you can be done with any mode essentially, so SHG or FLIM, Raman or PL. So yeah.
Thank you. And we have one more question that's just come in. So you've got two microscopes. Which would you recommend for semiconductor research?
I'll let Angela take that one.
So I guess as product manager, I should be able to answer this one. Both will perfectly work well for semiconductor research. It really depends on what you're specifically interested in. The RM5 is a much smaller instrument, so it will more easily fit into your lab. However, we are limited to Raman and photoluminescence only. If we're more interested in mapping full wafers, or we need additional techniques. So if you're looking at 2D materials, something like second harmonic generation is probably quite critical to your research. If you're wanting 360-degree polarization control in the excitation and the emission for both your Raman and your SHG and even your PL, again, this is where we'd be looking more for this RMS 1000 instrument. Essentially, it's very much going to depend on exactly what research you're looking at. So there's not a hard and fast RM5 or RMS 1000 rule, but RM5 would be better suited for sort of routine analysis on smaller devices that you're only really needing your Raman or your steady state PL from. Would move into the RMS 1000 if you were looking at larger wafers, so anything larger than 4 inches. And if you were needing extra techniques, so when we're looking to incorporate lifetime analysis or second harmonic generation, this is when we'd move more to the RMS 1000.
Okay, thank you. So there's solutions basically just based on what you need. So we have one last question, I think, unless any more come in. And that's if you want to use the Python IED for my own modeling, do I have to be good at coding or is it accessible to non-coders?
It's pretty accessible, yeah. So what what we would supply is, so on our Ramico home screen we have a bar at the top and it has Python and it's got a little button called favorite scripts. So you would just click on your favorite script and click run, and then it would do your analysis for you. You might have to do a little bit of jiggery pokery inside the code, maybe changing a number here or there, but it's it's very simple.
That's good. Good to know. There for anyone to use. So I think that concludes our webinar for today. Thank you, Angela and Matthew, for telling us about spectroscopic characterization of semiconductors. This webinar will be published on our YouTube channel for you to watch again, or you can share with colleagues who you think might find it useful. And we'll also be continuing this series next month, so make sure you subscribe to our newsletter to be the first to find out what our next episode will be about. And also, if you subscribe to our YouTube channel, you will get notifications of all of our latest videos. As Angela said, if you have any other questions, feel free to get in touch with us. So finally, thank you for joining us. We hope you enjoyed this session. We hope you found it useful, and we will see you next